Howdy! In this presentation, we're going to talk about stress and deflection caused by linear and bending impact. This is section 7.1 and 7.2 of your Machine Elements book. The objectives for today are going to be to, number one, understand the difference between static and impact loading, and number two, calculate the stresses and deflection due to impact loads. So now let's just think back on what we've done and covered in the class. Mostly everything having to do with static stresses. We went from internal load to internal stresses to combined loading of those stresses to stress transformation of those stresses to figure out principal stresses and maximum in-plane shear stresses, Mohr circle approach, and then we did 3D Mohr circle. Anyways, all of that was statics, and if you're wondering, we're talking about machines supposed to move. Where is the dynamic stuff? This is where it's coming from. So now we're shifting to, again, dynamic loading. In this presentation, we're going to talk about impact. On the next one, we'll do fatigue. So in engineering, impact loading is also sometimes called shock loading, sudden, or impulsive loading. When we think about impact loading, as we see below, usually we think as impact being something, bad or catastrophic, but that's not always the case. Sometimes we benefit from impact loading. So there are three categories of impact loads. And these categories are in increasing severity. Number one, rapidly moving loads of constant magnitude. Number two, suddenly applied loads. And number three, direct impact loads. So what is the difference? Again, number one is going to be the least severe. It's a rapidly moving load of constant magnitude. We would model this. The load is going to come from this mass over here. Mass times gravity is going to cause a load. And so what we have is in each of these mechanical analogs, the mass is what's going to be providing the impact, and the spring is going to be the structure that's going to be absorbing that impact. So just like a spring absorbs energy, right? That's our mechanical analog. Our structures are going to absorb the energy. Notice here we have a dashpot, and what the dashpot is doing is slowing down the mass as it's being accelerated to or into the structure or the spring. Suddenly applied load. This is the case where we have the mass and it's in direct contact with the spring or the structure. It's just barely touching it, and then what we're going to do is we're going to release this mass, and it's just going to kind of relax into the spring. It's going to do some bouncy things and then eventually stabilize. So we say that there's a instantaneous application of the full force mass times gravity. Yeah. Okay, the last one is direct impacts. What do we have? We have the same mass. There's no dashpot, and instead we have some distance between the mass and the spring. And what this distance is supposed to do is, one, give enough room for the mass to accelerate and then strike the structure. So it's like a full-blown impact. Here we will have the instantaneous application of the full force, right, of mass times gravity plus any kinetic energy before the strike. So we got the names, the mechanical analog. Some examples are for, again, an increasing severity, the lowest severity one, rapidly moving load. This is equivalent to if whenever you are like on a bridge, maybe you're crossing over to Mexico or crossing to South Padre Island, and then coming towards you on the other side, maybe you're standing on the bridge, there's a big semi, and as it rolls by, you feel the bridge kind of swaying or moving up and down. That's it's a rapid moving load. The load itself is being applied gradually. It's not static. The truck is not just sitting there. It's actually moving. So it causes a little of this impact load, but this is going to be the less severe. A suddenly applied load is like what the pistons inside an internal combustion engine feels. As you might know on an engine, right? The piston, well, depending on the number of strokes or whatever, at one point the piston compresses a mixture of air and gasoline or something that's flammable, diesel, there's a spark or ignition occurs, and then when that explosion goes, it is very fast, right? But it's not instantaneous. As the first spark starts going, the gases start heating up and expanding. It's fast, but it's not instantaneous. The last one is a direct impact load. So this is like, for example, if you're driving your car and then you smash into a wall, uh, direct impact load. So you have, again, a lot of kinetic energy, and then you hit all at once or instantaneously. So of course, we're talking about impact. It's dynamic loading. We talked about the statics, and we said, look, if it's instantaneous, it's the most severe. If it's gradual, then it's the less severe. And so the question should be, like, how slow can you go so that it's not like static, but it's actually considered now a dynamic or an impact load. So now to distinguish between dynamic, in this case impact loading, and static loading, what we're going to do is we're going to compare the time that it takes to apply the load from when it's not being applied to its full value, and we're going to compare it with the natural period of vibration of an undamped mass on a spring. Again, this is referring back to our mechanical models. So what is this period of vibration? Oh, this is what we call this tau, natural period of vibration. It's equal to 2 times pi times the square root of m by k, where m is the mass and k is the spring constant of whatever it is that it is receiving the blunt, right, the impact. When we look at this equation, we can say, hey, if we increase the m, right, or we decrease the k, or use not use, but if it strikes something that is of low stiffness, then we're going to get a bigger tau or a longer period of vibration. Why do we care about the period of vibration? Because if the time to apply the full loading is greater than 3 times the natural period of vibration, then it's considered a static loading. Now, if the time to apply the load is less than half the natural period of vibration, then it's considered dynamic loading. And so what happens then if it's been in between? Well, this is a quote-unquote gray area. This is between the time to apply the full loading is in between half a tau to 3 tau. If it's in between, it says in gray area. So first, let's cover the case where we have a dynamic loading. But before we do, let's look at what happens on a material when the loading rate changes. Because when we think of impact, usually you think of something that is, catastrophic and is wrong and is breaking stuff. But let's look at what happens to the material properties. One of the good things about increasing the loading rate is we can see here that the yield strength of a material is going to increase with the strain rate or loading rate. If we look at the ultimate strength, it also increases with the loading rate. However, when we look at the elongation, this is like the strain to failure, or how much the material deforms before it breaks or fractures, we see that it increases some and then it levels off. And here's the magic number here is about 10 to the 3 strain rate, this value. Usually in materials lab, I don't know if you remember, but we consider anything that is on strain rate of 10 to the 3 to 10 to the 5, this is your static. So if it takes that long, you're usually dealing with static. And if it's anything above, it's going to be this gray area and this dynamic. So the good thing is that as the loading rate is increasing, we got some material properties that are kind of helping us, the yield strength and the ultimate tensile strength, for example. The problem is when we look at the elongation to break, it remained constant. And actually what's going to happen is that this rapid loading is going to tend to promote a brittle failure. So the material is going to behave a little bit stronger. However, it's not going to plastically deform. Instead, it's just going to fracture and break. So we need to be careful and we need to account for that. Now, the tricky part with dynamic loading is sometimes just having a good measure of the time rate of the loading. Like how much time does it take for the loading to be applied? So sometimes the best we can do is just approximate this time loading. So we use empirically determined stress impact factors with the static strength properties. What does this mean? It means we're going to take the static properties of the materials and we're going to apply an impact factor or some magnification. So for example, in the past, engineers have used a stress impact factor of 4 in the design of automotive suspensions. So we didn't have with like a high degree of certainty, like what is the loading rates on the suspension. So instead we said, look, if we're expecting a force here static, normally it sees a force of, I don't know, a quarter of the car's weight. We're just going to multiply that times 4 and design those components that way. We'll see a little bit more on impact factors in the next couple of slides. But first, a very important difference between static and impact loading, and that is whenever we're designing parts or machine components to handle static loads, really we're designing to carry loads or stresses. But when we're designing parts that are going to be subject to the impact, then this must be designed to absorb the energy. Now remember this mechanical analog, the mass is going to have, some potential plus maybe some kinetic energy, and the spring, which is the component that's receiving all that energy, more than carrying a stress, it has to be able to absorb that energy without failure. Now, impact loads do not necessarily have to be compressive. We've been talking about compressing the spring on the mechanical analogs, but impacts can also be tensile. They could be in bending and torsion, or even we can do like combined loading or combination of these. So it can get complicated very quickly. So now that I got you all worried about impact, let's start with the worst case scenario just so we have a sense of how bad can it get. This is going to be the direct impact loads, or when a mass is going to struck an object with some kinetic energy. So for the case of direct impact loading, we're going to model it like so. So let's say we have a free falling mass of weight W over here that is going to impact the structure. So in this case, the structure is going to be modeled by the spring. The structure is assumed to be that it's going to respond elastically with a spring constant of K, which is in units of Newton per meter or pounds per inch, that sort of thing. Now, when the mass strikes the structure is going to deflect, and it's going to do so by some distance delta over here. So this is right when again, you're letting go of that mass, is going to hit the spring and it's going to compress it, and that's the maximum compression or the maximum value of the deflection of that spring. So what we're going to do in a little bit, remember impact, we have to deal with the energy transfer. So the mass being at some height above the structure had some potential energy, right, which is converted to kinetic energy, and then all that energy has to be absorbed by the spring. So we're going to do a little bit of math, but before, some assumptions. Assumption number 1 is that the mass of the structure, which is represented by the spring, is going to be negligible. Why we do this? This is so that the dynamic deflection curve or instantaneous deflection is going to be identical to that caused by the static application of the same load multiplied by an impact factor. So we're getting rid of dynamic effects from the spring by neglecting their mass. And instead what we're going to do is answer the question, how much? So if instead of an impact, we have this case over here on the second part, we have this weight, like how much do I need to magnify that force of that weight so that the spring would deflect the same amount as if it, as the amount that it would deflect if the mass directly hit it, right? So that magnification is going to be what we call this impact factor, and we'll show you how to calculate it in a little bit. But as a result of this assumption over here that the mass of the structure is negligible, in reality, the dynamic deflection curves is going to involve higher local stresses and deflections than the ones predicted by this simple approach. However, that's not the only assumption. Assumption number 2 is that the deflection within the mass itself is negligible. So what we're going to say is the mass is going to be completely rigid. Now we know in actuality the mass itself is going to deflect as well. So it also deforms, and when it does, it absorbs some portion of the energy. But we're going to go ahead and ignore this portion of energy in our calculations, and this is going to lead to slightly lower than predicted values of stresses and deflection. Remember, number 1 was going to underpredict. This is going to over. The third assumption that we're going to do is that the damping is negligible. Now, what's going to happen when the mass hits the structure, right? There's internal friction in the spring, and so some energy is going to be lost to this friction. So not all of it is going to be elastically stored in the spring, but we're going to go ahead and neglect this. And so this is going to lead again to slightly lower than calculated stresses and deflection. So again, what we have is a mass here of weight W that is going to directly impact a structure, in this case the spring. When it does, right, the spring is going to deflect by a delta amount. And what we want to calculate is what is Fe, or what is the equivalent static force, because we're used to dealing with static forces, right? What is the equivalent static force that would produce the same deflection delta? So the same deflection that the direct blow or impact gives. Now, one of the quantities that we're going to work with is delta St. What is delta St? This is the static deflection after the energy is dumped out. So if I have this weight and I let it drop, right, it's going to bounce, bounce, bounce. Eventually it's going to stabilize. And that static deflection, a little bit, is going to be a lot less than this delta, is how much the spring would deflect if I just let the mass lie on top of the spring and give it all the time in the world to equilibrate. Again, what's going to happen, right, is this mass, when it's up here before it hits, right, it has some potential energy. And so all that potential energy on the mass has to be absorbed by the spring. So how much is the potential energy in the mass? Well, recall the equation. Potential energy U equals mg times delta H, right? Mg is mass times gravity. So we already have the weight is the same thing as mass times gravity. And delta H is how much did that object drop? Well, here, the height that the object is dropping is not only H over here, but notice when it drops, right, it doesn't stop right here. It also causes a little bit of deflection, delta, so that the total drop is H plus this delta. So if we want to calculate the energy, remember energy is just force times the distance. So the force is going to be provided by the weight, mass times gravity, and then the distance is going to be the height H, right, which is this guy, plus the little bit of give from the spring. And so all of this here in dark blue is the potential energy given by the falling mass. Not all that energy has to be transferred to the spring, right? So in the spring, we know initially there's no deformation. So let me do the spring in maybe purple. Deflection is 0. And then when the mass hits it at the maximum deflection point, it's going to deflect an amount of delta. Now the force is going on the spring is going to go from 0, because right here before it touches, right, the force is 0. And then once it hits, it's going to amplify it to this big force over here, which we call the equivalent static force. Now, when we look at this triangle, the area underneath the curve, that's going to be the energy absorbed by the spring. So, right, that's equal to 1/2 Fe times delta, or 1/2 the base times the height. So now, setting up the equation, again, what we have is the potential energy from the falling mass. Remember, potential energy is mass times gravity times the drop height. Mass times gravity is the same thing as the weight here, right? And the total drop height is h plus the delta, or the distance between when the mass first hits the spring and then plus how much the spring gives away, right? That's a potential energy. That has to be equal to the energy absorbed by the spring. What is the energy absorbed by the spring? So make a plot over here of force times deflection. When that mass first hits the spring, right, when it first makes a contact, right, just before it touches, the force is 0. And then because the spring is linear, as the mass is being forced or driven into the spring, the force is increasing up to a maximum value, right? And this maximum value is this equivalent force. How much did the spring deform? Well, it's this value delta. Now, the energy absorbed in the spring is the area underneath the curve. Hopefully you remember that from materials. So in this case, the area, which is just this over here, is the area of the triangle. 1/2 the base, which is delta, times the height, which is Fe, right? 1/2 Fe delta. That's this part over here. Next, we're going to do a little bit of algebra, but first let me remind you the equation of a spring, and that is that the force is proportional to the deflection. F equals Ks from statics. In this example, right, the force specifically is going to be the equivalent force over here, right? Multiply times K, and it's not S, but it's delta, the dynamic deflection. So that gives us this first little equation. Next, you might ask yourself, what is this K value, right? The spring constant. We can solve for the spring constant K from this equation, right? Up on top, K is just F by the deflection. So in our case, how can we calculate the spring constant? Well, the force is just the weight of the mass, and if we measure the static deflection, that is if we apply that mass, that weight, let it rest on the spring, is going to deflect some little amount, the static deflection. So we can use that to figure out what this spring constant is, which gives us this equation over here, which means we can write the equivalent force, right, as K times delta, but K is just W by the static deflection. So that's our K, and then multiply times delta. So if then we take this equation or this expression for Fe and we substitute it over there, what do we have? So we're going to have 1/2 Fe, but Fe is just W times delta divided by delta St times delta, right? And it's going to give us this one over here, 1/2 delta squared W by the static deflection. So just a little bit of algebra to get over here. On this other side, we still have the potential energy. This is a quadratic equation for delta, for this delta. C is quadratic because it's to the second power. So we can actually solve that quadratic equation for delta, and the solution looks like this. So delta is the static deflection times 1 plus the square root of 1 plus 2h divided by delta st. Now, if we look closely, this equation, I put all of this in parentheses in a different color. It's a light blue. This quantity in parentheses is what we call the impact factor. This is the factor by which the load, stress, and deflection caused by the dynamic applied load W exceed those by the slow static application of the same weight. Oh yeah, this still sounds too fancy. What this means is if I take the static deflection, delta ST, and I multiply it by this number in the parentheses, I can calculate the dynamic deflection, or how much the spring is going to give from the direct impact loading. Similarly, I can multiply the weight, right, of that initial mass that is hitting the structure by the same impact factor, and this is going to give me the equivalent force, the equivalent static force that I would need to apply to cause the same deflection as the impact load. Now these equations above are in terms of h, or the drop height, but remember we can rewrite this in terms of velocity, because if we have a mass, right, that is falling down with some acceleration, in this case the one provided by gravity, I can rewrite this instead of a drop height in terms of a striking velocity over here. And I have this on the bottom, so I have that delta, this is the dynamic deflection, is equal to the static deflection times this over here in parentheses, which is the impact factor, but now written in terms of a terminal velocity, in terms of the velocity v. That's the velocity at which the mass is going to strike the object. So we have that equation, and we have this one over here for Fe. This is going to tell us the equivalent static force that I would need to apply to the structure so it causes the same deflection. That's just going to be the initial weight of our mass times this impact factor. Now we can further simplify this impact factor by noting that in many problems that involve impact, the deflection delta, or how much the spring gives, is so smaller compared to h, the height from which that object gets dropped, that we can simplify this impact factor to just these equations, right? So how we do that? Well, let's take this delta st, multiply it, we'll have delta st plus the square root, and I'm going to take this delta st and I'm going to stick it inside, all right? So it's going to be delta st squared plus 2h delta st squared divided by delta st, right? And if delta st is almost 0, right, this is going to go to 0, this guy's going to go to 0, and the delta st at the bottom cancels with 1 on the top, and so we would only have the square root of twice the height times delta st. If we follow kind of the same approach for the equivalent force, it's going to simplify to this one. And if we're working with the equations in terms of velocity, they're going to simplify to this other ones over here. Alrighty, so next I have an example. I'm calling example 7.1. It has to do with an elevator that kind of jerks, similar to the one we have in the engineering building right now. But anyways, you'll see that it's rather easy to do this impact loading problems. They're a lot easier to do than what the theory sounds from the previous slides. But I want to go ahead and do this one by hand because there's not enough room and it's not easy to write with the pen on the computer. So look for this example on a separate video. In general, the solution procedure for direct impact loads is going to be as follows. The first step that we're going to take is we're going to determine if from the information given, if they give us a drop height or a velocity, right? Because we have equations for impact factors in terms of drop heights and velocities. So we need to know which one of the two we're working with. Next, we want to calculate the static deflection, delta ST, because that value, that static deflection, is used to calculate the impact factor. So regardless of which equations we're going to use, we need to determine the static deflection. Remember, that one is if whatever is striking our object, we go ahead and place it slowly and give enough time, and we just calculate how much does that structure give. That's the static deflection. So we'll calculate that, and once we have that, and we know if we're working with h's or v, I mean heights or velocities, we can go ahead and calculate the impact factor, which is the quantities inside the parentheses. You'll go ahead and want to calculate that quantity, which is going to be a value greater than 1. And then we're going to use that value, that impact factor, to calculate the maximum stress and the maximum deflection. So the maximum deflection is going to be given by this delta formulas. This is going to give us the maximum deflection, or the deflection from the direct blow into the structure. The maximum stress, well, that's going to depend. And I say depend because we can have something that is loaded under axial loads, right? So in this case, the stress is just P by A. Instead, what we're going to use, instead of a load P, we're going to use this equivalent force in there, right? So that's in the case if it's axial load. We could also have a beam and bending. We'll do an example with that one. But again, that comes from the equivalent force, which is just the weight of the object that is striking times, again, that impact factor. It's easy, so look out for those videos. Let's move on. Oh, I have the answer here. Next, I have a class activity. So this class activity is the same. It looks different, but it gets solved the same way. So if you want to go ahead and stop the video right now, look at that example 7.1, and then see if you can work this example and see if you get these answers over here. Next, let's talk about impact energy capacity. Remember, why do we care about the impact energy? Well, because whenever we have some impact, what we're doing is we're transferring the energy, and whatever is receiving has to have the capacity to absorb it. If it doesn't, it's going to break, there's going to be some failure. So the impact energy capacity of a straight rod is going to be a function of its volume. So this energy or capacity is equal to sigma squared times V, where V is the volume. Oh, it's written over here, sorry. Is the volume of the material divided by twice the elastic modulus. Now, we can use this equation to calculate two things. We can calculate, hey, how much energy was absorbed by the straight rod if instead of putting sigma, we put this quantity for sigma. We put the equivalent force divided by the cross-sectional area. So we put this in that equation, the U is going to be the energy absorbed. If we want to calculate the elastic energy capacity, like how much the maximum, the energy that a straight rod can take, then instead of sigma up there, we use the value for the yield strength of the material. So if we put the value of the yield strength for the material up there, it's going to give us the energy capacity because we can stress it only all the way up to the yield strength. If we put the actual or the stress that the material was seeing, again, that's going to be the equivalent load by cross-sectional area, then it's going to tell us how much energy was absorbed from that impact. Next, I have example 7.2, which deals with bending impact. Here we have a mass that is striking a beam over here. The beam is going to deflect and is asking us to determine the maximum stress and deflection of the beam. Again, I'll have, I have the answers here at the bottom, but I'll go ahead and explain this one also on its own separate video. So look for that other video as well. All right, so we covered already the worst case scenario, which is the direct impact. Next, let's go with the one that follows in severity. So the next less worse scenario. Oh my God, my English is horrible. This is the suddenly applied load. This is where the mass is not dropping into the spring. Instead, the mass is like barely touching the structure, and then you let go of the mass. I like to give the example of maybe if you ever gone tailgating. So you pop the tailgate open on the truck, and you kind of put your like right before you sit on that tailgate, right? You're real close, and then you let yourself go, and the truck is gonna do some little bouncy back and forth. This is the like one equivalent of a suddenly applied load, where the mass, in this case our body, right, it's almost touching that tailgate, and then you just let yourself rest. Anyways, so how do we deal with this one? Super simple, right? Why? Because what is going to be the H over here? We have the equations already for the impact factor, and so what is the H, or the drop height, or what is the the H over here? Well, the H in this case is 0 because the mass is already touching, right? So if H is 0, then this quantity goes to 0, and instead we have the square root of 1 plus 1, that gives us 2. So that tells us that the impact factor for a suddenly applied load when the mass is just touching, but it's still some dynamic, is just twice. Or, yeah, twice. What does that mean, right? If we're working for the equivalent force, right? For a suddenly applied load, that's just going to be the weight of the mass, right? Times 2. I mean, I don't know what else to say other than just multiply by 2, and you're already accounting for the case of a suddenly applied load. That's pretty much it. Let's go to the next slide. So now we have the best case scenario under impact loading, which means the least severe, and that is the case for a rapidly moving load. This is when, yes, the mass is touching the spring, right? So H is also 0, but then there's something else slowing it down. So we already saw for the previous case that the impact factor is 2. So what is the impact factor in this case? The book doesn't provide an answer. It's got to be between 1 and 2. So here my advice for you is, if you're worried about impact, right, but it's not a direct impact, if you go with an impact factor of 2, that means if you design for double the load or double the deflection, then you're overkill, because yeah, this is not even accounting for something that is slowing down. So that's it. Just at least an impact factor of 2 and you'll be fine. Now, there are other types of loading can also cause impact. Next, I have some slides for torsional impact. It's not in the original title of the presentation, but I'll just put here a couple just to show you the similarities. It's almost the same thing, except we're changing from a linear motion, like an up and down or something striking linear motion, to a torsional, or something that is rotating. So instead of, for example, having a deflection, in meters or inches, the deflection, because we're talking about stuff that is rotating, is going to be in angles, in radians. Instead of having an equivalent static force, we're going to have an equivalent static torque. Instead of a mass, this is going to be a moment of inertia, because now you have, again, stuff that is rotating. And then we're going to have a spring rate, which is K. Instead of an impact velocity, we can have, in linear terms, right, meters per second, we're going to have an impact velocity, but it's rotational, right? So it's radians per second. And then the energy absorbed, or kinetic energy, is going to be the same. And so without going into too much details, again, instead of having like a static deflection, right, like how much is going to give, this is in radians, and that's going to be equal to the square root of 2 times u, that is this rotational energy, divided by k, or the spring constant. What is u in this case? Well, we'll use the rotational kinetic energy, or 1/2 I times omega squared, where omega is that, what do you call this, rotational velocity. And then what is K? We can figure out K is like a spring constant, but in torsion. Over here, which takes the form for a solid round bar. K is going to be equal to pi d fourth, d to the fourth times g divided by 32L, and g is going to be your shear modulus, or modulus of rigidity. So if you want to calculate the maximum torsional stress, then we'll use this equation over here, where tau is 2 times the square root of u times g divided by b. Again, u is rotational kinetic energy, g is going to be the shear modulus, and b is going to be the volume of a solid round bar. So I used to go over this example that is in the book, where you have this grinder. So there's a motor here that is spinning, and there's 2 grinding wheels, and then something happens that one of the wheels gets jammed, right, and the other one, I forget which one, gets jammed on this problem, but the other one has some inertia that wants to keep spinning, right, and so it kind of momentarily twists or over torques the shaft over here, and we can estimate the angle of deflection and the torsional over here. Again, I'm not going to go over it. I don't even have homeworks for you to practice, but you got the equations on the prior slide. If you want, you can give it a try and see if you get the same deflection angle and torsional stress. Alrighty, so besides those other example videos, that's all I have. So if it's not making sense right now, I guarantee you that after you see the examples, it's going to make perfect sense. So anyways, I hope you learned something today, and we'll see you on the next one.